Aldehyde, Wikipedia audio. An aldehyde/AELDHAD/ or alkanal is an organic compound containing a functional group with the structure CHO, consisting of a carbonyl center with the carbon atom also bonded to hydrogen and to an R group, which is any generic alkyl or side chain. The group without R is the aldehyde group, also known as the formyl group. Aldehydes are common in organic chemistry. Many fragrances are aldehydes. Aldehydes feature an sp2 hybridized, planar carbon center that is connected by a double bond to oxygen and a single bond to hydrogen. The CH bond is not ordinarily acidic. Because of resonance stabilization of the conjugate base, an alpha hydrogen in an aldehyde is far more acidic, with a pKa near 17, compared to the acidity of a typical alkane. This acidification is attributed to the electron withdrawing quality of the formyl center and the fact that the conjugate base, an enolate anion, delocalizes its negative charge. Related to, the aldehyde group is somewhat polar. Aldehydes can exist in either the keto or the enol tautomer. Keto-enol tautomerism is catalyzed by either acid or base. Usually the enol is the minority tautomer, but it is more reactive. Structure and bonding. The common names for aldehydes do not strictly follow official guidelines, such as those recommended by IUPAC, but these rules are useful. IUPAC prescribes the following nomenclature for aldehydes. The word aldehyde was coined by Justus von Liebig as a contraction of the Latin alcoholdehydrogenatus. In the past, aldehydes were sometimes named after the corresponding alcohols, for example, vinous aldehyde for acetaldehyde. The term formyl group is derived from the Latin word formica ant. This word can be recognized in the simplest aldehyde, formaldehyde, and in the simplest carboxylic acid, formic acid. Aldehydes have properties that are diverse and that depend on the remainder of the molecule. Smaller aldehydes are more soluble in water, formaldehyde, and acetaldehyde completely so. The volatile aldehydes have pungent odors. Aldehydes degrade in air via the process of autoxidation. The two aldehydes of greatest importance in industry, formaldehyde and acetaldehyde, have complicated behavior because of their tendency to oligomerize or polymerize. They also tend to hydrate, forming the geminal diol. The oligomers/polymers and the hydrates exist in equilibrium with the parent aldehyde. Aldehydes are readily identified by spectroscopic methods. Using IR spectroscopy, they display a strong nu CO band near 1700 cm 1. In their 1H NMR spectra, the formyl hydrogen center absorbs near delta H equals 9, which is a distinctive part of the spectrum. This signal shows the characteristic coupling to any protons on the alpha carbon. Important aldehydes and related compounds. The aldehyde group is colored red. From the left, formaldehyde and its trimer 1,3,5-trioxane, acetaldehyde and its enol vinyl alcohol, glucose, the flavorant cinnamaldehyde, the visual pigment retinol, and the vitamin pyridoxal. Traces of many aldehydes are found in essential oils and often contribute to their favorable odors, e.g. cinnamaldehyde, cilantro, and vanillin. Possibly because of the high reactivity of the formyl group, aldehydes are not common in several of the natural building blocks, amino acids, nucleic acids, lipids. Most sugars, however, are derivatives of aldehydes. These aldoses exist as hemiacetals, a sort of masked form of the parent aldehyde. For example, in aqueous solution only a tiny fraction of glucose exists as the aldehyde. There are several methods for preparing aldehydes, but the dominant technology is hydroformylation. Illustrative is the generation of butyraldehyde by hydroformylation of propene. Nomenclature. Aldehydes are commonly generated by alcohol oxidation. In industry, formaldehyde is produced on a large scale by oxidation of methanol. Oxygen is the reagent of choice, being green and cheap. In the laboratory, more specialized oxidizing agents are used, but chromium reagents are popular. Oxidation can be achieved by heating the alcohol with an acidified solution of potassium dichromate. In this case, excess dichromate will further oxidize the aldehyde to a carboxylic acid, so either the aldehyde is distilled out as it forms or milder reagents such as PCC are used. Oxidation of primary alcohols to form aldehydes can be achieved under milder, chromium-free conditions by employing methods or reagents such as IBX acid, des-Martin-periodinane, Swern oxidation, tempo, or the Oppenauer oxidation. Another oxidation route significant in industry is the Wacker process, whereby ethylene is oxidized to acetaldehyde in the presence of copper and palladium catalysts. On the laboratory scale, alpha-hydroxy acids are used as precursors to prepare aldehydes via oxidative cleavage. Aldehydes are highly reactive and participate in many reactions. From the industrial perspective, important reactions are condensations, e.g. to prepare plasticizers and polyols, and reduction to produce alcohols, especially oxoalcohols. From the biological perspective, the key reactions involve addition of nucleophiles to the formyl carbon in the formation of imines and hemiacetals. The formyl group can be readily reduced to a primary alcohol. Typically this conversion is accomplished by catalytic hydrogenation either directly or by transfer hydrogenation. Stoichiometric reductions are also popular, as can be effected with sodium borohydride. The formyl group readily oxidizes to the corresponding carboxyl group. The preferred oxidant in industry is oxygen or air. In the laboratory, popular oxidizing agents include potassium permanganate, nitric acid, chromium oxide, and chromic acid. The combination of manganese dioxide, cyanide, acetic acid, and methanol will convert the aldehyde to a methyl ester. IUPAC names for aldehydes. Etymology. Another oxidation reaction is the basis of the silver mirror test. In this test, an aldehyde is treated with Toland's reagent, which is prepared by adding a drop of sodium hydroxide solution into silver nitrate solution to give a precipitate of silver oxide, and then adding just enough dilute ammonia solution to redissolve the precipitate in aqueous ammonia to produce 2+ complex. This reagent will convert aldehydes to carboxylic acids without attacking carbon-carbon double bonds. The name silver mirror test arises because this reaction will produce a precipitate of silver, whose presence can be used to test for the presence of an aldehyde. Physical properties and characterization. Applications and occurrence. Naturally occurring aldehydes. Synthesis. Oxidative routes. A further oxidation reaction involves Felling's reagent as a test. The Cu2+ complex ions are reduced to a red brick-colored Cu2O precipitate. If the aldehyde cannot form an enolate, addition of strong base induces the Cannizzaro reaction. This reaction results in disproportionation, producing a mixture of alcohol and carboxylic acid. Nucleophiles add readily to the carbonyl group. In the product, the carbonyl carbon becomes sp3 hybridized, being bonded to the nucleophile, and the oxygen center becomes protonate. Specialty methods. In many cases, a water molecule is removed after the addition takes place. In this case, the reaction is classed as an addition, elimination or addition, condensation reaction. There are many variations of nucleophilic addition reactions. In the acetalization reaction, under acidic or basic conditions, an alcohol adds to the carbonyl group and a proton is transferred to form a hemiacetal. Under acidic conditions, the hemiacetal and the alcohol can further react to form an acetal and water. Simple hemiacetals are usually unstable, although cyclic ones such as glucose can be stable. Acetals are stable, but revert to the aldehyde in the presence of acid. Aldehydes can react with water to form hydrates, RCH2. These diols are stable when strong electron withdrawing groups are present, as in chloral hydrate. The mechanism of formation is identical to hemiacetal formation. In alkyliminodeoxo by substitution, a primary or secondary amine adds to the carbonyl group and a proton is transferred from the nitrogen to the oxygen atom to create a carbonylamine. In the case of a primary amine, a water molecule can be eliminated from the carbonylamine intermediate to yield an imine or its trimer, a hexahydrotriazine. This reaction is catalyzed by acid. Hydroxylamine can also add to the carbonyl group. After the elimination of water, this will result in an oxime. An ammonia derivative of the form H2NNR2 such as hydrazine or 2,4-dinitrophenylhydrazine can also be the nucleophile and after the elimination of water, resulting in the formation of a hydrazone, which are usually orange crystalline solids. This reaction forms the basis of a test for aldehydes and ketones. The cyano group in HCN can add to the carbonyl group to form cyanohydrins, RCHCN. In this reaction the CN ion is the nucleophile that attacks the partially positive carbon atom of the carbonyl group. The mechanism involves a pair of electrons from the carbonyl group double bond transferring to the oxygen atom, leaving it single bonded to carbon and giving the oxygen atom a negative charge. This intermediate ion rapidly reacts with H+, such as from the HCN molecule, to form the alcohol group of the cyanohydrin. Organometallic compounds, such as organolithium reagents, Grignard reagents, or acetylides, undergo nucleophilic addition reactions, yielding a substituted alcohol group. Related reactions include organostanane additions, Barbie reactions, and the Nozaki-Hayamakishi reaction. In the aldol reaction, the metal enolates of ketones, esters, amides, and carboxylic acids will add to aldehydes to form beta-hydroxycarbonyl compounds. Acid or base catalyzed dehydration will then lead to alpha-beta unsaturated carbonyl compounds. The combination of these two steps is known as the aldol condensation. The Prince reaction occurs when a nucleophilic alkene or alkyne reacts with an aldehyde as electrophile. The product of the Prince reaction varies with reaction conditions and substrates employed. Common reactions. Aldehydes characteristically form addition compounds with sodium bisulfite. This reaction is used as a test for aldehydes. Reduction. A dialdehyde is an organic chemical compound with two aldehyde groups. The nomenclature of dialdehydes have the ending dial or sometimes dialdehyde. Short aliphatic dialdehydes are sometimes named after the diacid from which they can be derived. An example is butanediol, which is also called succinaldehyde. Some aldehydes are substrates for aldehyde dehydrogenase enzymes which metabolize aldehydes in the body. There are toxicities associated with some aldehydes that are related to neurodegenerative disease, heart disease, and some types of cancer. Oxidation. Nucleophilic addition reactions. Oxygen nucleophiles. Of all aldehydes, formaldehyde is produced on the largest scale, about 6 million tons per year. It is mainly used in the production of resins when combined with urea, melamine, and phenol. It is a precursor to methylene diphenyl diisocyanate, a precursor to polyurethanes. The second main aldehyde is butyraldehyde, of which about 2,500,000 tons per year are prepared by hydroformylation. It is the principal precursor to 2-ethylhexanol, which is used as a plasticizer. Acetaldehyde once was a dominating product, but production levels have declined to less than 1 million tons per year because it mainly served as a precursor to acetic acid, which is now prepared by carbonylation of methanol. Many other aldehydes find commercial applications, often as precursors to alcohols, the so-called oxo-alcohols, which are used in detergents. Some aldehydes are produced only on a small scale and are famously used as ingredients in flavors and perfumes such as N Degree 5 from Chanel. These include cinnamaldehyde and its derivatives, citral, and lilol. Nitrogen nucleophiles. Carbon nucleophiles. Bisulfite reaction. More complex reactions. Dialdehydes. Biochemistry. Examples of aldehydes. Examples of dialdehydes. Uses.